Today we are going to study the explanation of Stern-Gerlach experiment in terms of vector space algebra. Now what happens in Stern-Gerlach experiment? In Stern-Gerlach experiment, magnetic field B interact with the magnetic moment of the AG atom. How it interact? Now it will exert some force on the magnetic field. As we know, the expression of the field will be F equal to gradient of minus mu of P. This is the interaction energy. Interaction energy of that AG atom, which has a magnetic moment mu, and an external magnetic field B is applied on that AG atom. Now suppose that B is in the direction of Z. Suppose the direction of the B is in Z direction. Then the interaction energy E will be minus mu Z B. Now mu Z will be the Z component of the magnetic moment of the AG atom. Now this will be the this mu Z should proportional to the Sz. Sz is the spin momentum corresponding to Z direction. Now as we know from our previous lecture that after being measured or after being interact with this observable Sz or with Sz, the state of the AG atom will be thrown into one of the eigenstates of the sigma Z observable. We know from the Stern-Gerlach experiment that sigma Z has only two eigenstates. One is plus, which is corresponding to in the direction of the magnetic field, and other is the minus, which is in the opposite direction of the magnetic field. Now the AG atom will be on one of these two eigenstates after being passed through the magnetic field, and this sigma Z can be represented in terms of matrix. The representation of sigma Z in matrix is 1 0 0 minus 1. Then this state will be in matrix form 1 0, and this state will be 0 1. And similarly the sigma x, the matrix representation of sigma x is 0 1 1 0, and the normalized eigenvalues corresponding to sigma x will be 1 by root 2 1 1 and minus plus 1 by root 2 1 minus 1. These eigengates corresponding to the eigenvalue plus h cut by 2 when we measure the x component of this spin, and when we will measure the x component of this spin, we will get minus h cut by 2 when the state will be in these eigengates, and here there will be an h cut by 2, and here also there will be a h cut by 2. Now, and again sigma, similarly sigma y, the representation of the sigma y in matrix form is h cut by 2 0 I minus I 0, and the eigengates are normalized to eigengates are 1I and we can write eigengates of sigma x or sigma y in terms of sigma z. We can write eigengates of any of these operator in terms of any eigengates of other two operators, because these operators or these observables are Hermitian observables, and normalized eigengates will be the span of the whole eigengate. So we can express any eigenvectors in this eigenspace in terms of any of these eigengates of sigma z or sigma x or sigma y. So we can write plus sx in terms of sz as follows: sz plus similarly we can write minus sx will be 1 plus 1 sz minus sz. Similarly, we can write also the eigengates of sy in terms of sz as follows: plus minus sy equal to 1 by root 2 plus sz plus minus I minus z. So that is that. And now we can ask a question that if suppose an Ag atom, that randomly oriented Ag atom sent into an Stern-Gerlach apparatus in which a external magnetic field applied in the z direction, after passing through the magnetic field, the Ag atom will be split into two parts, and if the intensity of the Ag atom will be I0, in entrance, then after passing through this Stern-Gerlach experiment apparatus, it will be divided in these two stream. One's intensity will be I0 by 2 and other's intensity will be I0 by 2. Now if we block, suppose this is corresponding to minus z sz and this is corresponding to plus sz. Now if we block one of the stream and then next we will pass it through another apparatus in which the magnetic field applied in the x direction. Now what will be the intensity that will found Ag atom in plus Sx and plus minus Sx. That means what will be the intensity that we will find the Ag atom after passing through this SGA apparatus, what amount of Ag atom will be found in the direction of magnetic field and what fraction of what intensity of the Ag atom will be found in the opposite direction of the magnetic field. Now since we can write the state Sz in terms of Sx as 1 by root 2 plus Sx plus minus Sx, then what will be the probability after observing it, after measuring it by an observable Sx, then what will be the probability that it will be found one of the eigenkets of this observable Sx plus Sx? That probability, as we know from our previous lecture, that this will be the plus Sx plus Sz square, and what it will be? It will be 1 by 2 into plus Sx into plus Sx plus minus Sx. And since these two are orthogonal state, then that means this will give us one orthonormal state and this will give back as 0. So that means the intensity after passing through these apparatus will become half and half. So what will be the intensity that will get Ag atom in direction of the magnetic field after passing this Stern-Gerlach apparatus will be I0 by 4 and I0 by 4. So we will explore this concept in the mathematical section of our lecture later. Now we'll study another important concept, which is compatible observable. Now what is compatible observable? If there are two observable A and B, suppose we measure a state alpha with A first, some measurement which observe the observable corresponding to A and get back A, and then the state will be thrown into one of its eigenkets, suppose A, and if then we measure another observable B, it will get B and the state will be thrown into eigencase of this observable B. Now if we measure B first then A, then we'll get, if we will get same measurement result of measurement values, then we will say that A and B are compatible operators. Suppose if we measure in this direction alpha B first, then we will get the same measured value, same measured value as we get previously when we first observe A then observe B, and if we again in this state observe A, we will get the same measure value as we observed previously. So that means the observable A does not interact with the information measured by B, or vice versa, that is B does not interact with the measured information of A. So if it is happen, then these two operators are called compatible operators. Mathematically we write A comma B equal to 0. That means AB minus BA equal to 0. This is the mathematical condition for compatibility, and if it doesn't hold AB not equal to BA, then it is called incompatible operator. If some operators are incompatible, then if we measure two observable one by one, then there will be some uncertainty corresponding to that measurement, and we will see that uncertainty in the later section of our lecture, in the next lecture. Now we'll going to ask a question that, as we know, if since A and B are observable, then these are Hermitian operators. And we know the eigencase of the Hermitian operator are orthogonal, and we can make it orthonormal also. We can make it the eigencase orthonormal. That means we can span the whole Kate space by any of the two operator A or B. Now our question is, what is the relation between the eigengates when A and B are compatible operators. Before answering the same question, we must touch upon a very important concept called degeneracy. What is degeneracy? Suppose two linearly independent eigenstates of A have the same eigenvalue, then these two eigenstates are called degenerate eigenstate, and this is called degeneracy. What this means, if two eigenstates, suppose that A alpha A alpha and another eigenstate alpha prime has the same eigenvalue, and these two are linearly independent, then these two eigenstate are called degenerate eigenstate. Now when I prove the orthogonality of the eigenstates, we assume that the eigenvalues corresponding to different eigenstates are not same in general, alpha not equal to beta. If there are two eigenstate alpha and beta, then alpha not equal to beta, we assume that. But for degenerate observable, alpha can be equal to beta when these two states are linearly independent. Now if it happens so, then our concept of orthogonality in case of eigenstates become difficult. Now how can we solve this problem? And there is a second problem corresponding to this, that for the representation purpose, now if the two eigenstates have the same eigenvalue alpha, then we cannot represent the two linearly independent eigenstates in terms of alpha. Then how can we distinguish these two linearly independent eigenstates how can we represent those two linearly independent eigenstates? Now for this situation, fortunately in quantum mechanics eigenvalues of some corresponding eigenvalues corresponding to some compatible observable say B can be used to keep a level. So how we do so that level does this state with some compatible observable eigenvalue of some compatible observable will show in this later section. Now there is a theorem in quantum mechanics. Suppose A and B are compatible and A has non-degenerate eigenvalues, non-degenerate eigengates is then the representation of B in the eigengates of A will be diagonal, which means that if we represent the B in terms of the normalized eigengates of A, orthonormal eigengates of A, the B will be a diagonal matrix. Now we will going to prove the theorem. Now suppose that A dash and A double prime are two eigengates of A, then A comma B double prime will be A double prime AB minus BA A prime, that will be A double prime AB A prime minus A double prime BA A prime. This will be A double prime B A prime minus this will be A prime A double prime B A prime. Now this will be A double prime minus A prime A double prime B A prime. Now from this, since this A and B operator are compatible, that means A comma B equal to 0. That means A double prime A comma B will give us 0. So that means either A double prime minus A equal to 0 or A double prime B A prime equal to 0. Since since the eigengates are non-degenerate, that means all eigenvalues corresponding to all eigengates are different. That means A double prime and A prime not equal to 0 if A double prime not equal to A. That means this will be 0 if A prime not equal to A double prime. That means then it will be 0. And if A double prime equal to A equal to 0, that means then this itself becomes 0. This product becomes 0, then the whole product becomes 0. That means A double prime B A prime will be delta A prime to A double prime B A double prime. Now the representation of the B in terms of eigengates of A will be B will be summation of A prime A double prime A double prime B A prime and A prime. Now if we write this value here, then we'll get A prime, A double prime, A double prime, A prime, delta A double prime, A prime, A double prime into A double prime B A double prime. That means this will be A double prime, A double prime, A double prime, A double prime B A double prime. Observe the value of the observable B corresponding to any eigengates of the operator A will get double prime double prime A into A double prime B A double prime. That means we'll good, since the eigengates are orthonormal, that means it will be delta A, delta conical delta. That means this will be A double prime delta A double prime B A double prime. That means it will be A B A. That means A is a eigenvalue. A is also the eigengates of B, and eigenvalue corresponding to the eigengates will be the this B equal to A B A. Expectation value of B in the eigengates of operator A will be the eigenvalue corresponding to the same eigengates of the operator A. That means these A eigengates are the simultaneous eigengates of the two operators. Simultaneous of the two operator A and B. A and B. Then we can represent any state in terms of A comma B, where A is the eigenvalue corresponding to operator A and B is the eigenvalue corresponding to operator B, and this is the state of the system. Now if we operate with A, we will get eigenvalue A and the system will remain in the same state, and the state B will this simultaneous state will not change, and if we operate with B, it will give us